We are now going to look at a few examples of functions for which we will try to find the vertical asymptotes. Let's say we want to find the vertical asymptotes for the function f of x, which is equal to 1 over 2x squared plus x minus 3. Remember that we have a vertical asymptote when the limit of the function is infinite, at least for one of the one-sided limits. Since this function is a rational function, its limit is obtained by plugging x equal a in the function at any a that is in the domain of this rational function. That means that the only way for the limit to be infinite, in other words, for the limit not to exist, is for a to fail to be in the domain of the function. In other words, for a rational function, the only place where we could have a vertical asymptote is for x equal a, where a is a zero of the denominator. So we look for the zeros of the denominator. In other words, we factor the denominator. Here we get that the function is 1 over x minus 1 multiplied by 2x plus 3. This product is 0 if one of the factors is 0. In other words, if x equal 1, or if 2x plus 3 equals 0, that is, x equal negative 3/2. Let's look at what happens at x equal 1. If x is approaching 1, the top doesn't change, it's 1, and the bottom x minus 1 is approaching 0. So we have something that is a constant divided by something closer and closer to 0. The values are going to grow without bounds. In other words, we're going to find an infinite limit at 1. The geometric interpretation is that x equal 1 is an asymptote for this function. Similarly, if we look at what happens when x gets closer and closer to negative 3/2, then 2x plus 3 gets closer and closer to 0, but the top remains 1. So we get 1 over something closer and closer to 0. Again, the values grow without bounds. And we get that x equal negative 3/2 is an asymptote. From this example, you may think that to find the vertical asymptotes, you only need to find the zeros of the denominator, and for each such zero, x equal this value would be a vertical asymptote. It's not exactly that simple. Let's look at a second example to see what kind of problem we may run into. Let's say we are looking for the vertical asymptotes of the function 2x squared plus 3x minus 5 divided by x squared plus x minus 2. It's again a rational function, and by the same argument as before, the only place where we may have a vertical asymptote are for values of x where the denominator is 0. So we're going to look for the zeros of the denominator by factoring it. We find that x equal 1 and x equal negative 2 are the two zeros of the denominator. But before we conclude that x equal 1 and x equal negative 2 are two vertical asymptotes, we need to check that indeed for these values of x we have an infinite limit. When x equal 1, you see that if I plug x equal 1 at the top, I get 2 plus 3, 5 minus 5, 0. That means the top is also 0 at x equal 1. But it's a polynomial. That means x minus 1 is a factor at the top. Now, if we look at what it means for the limit of f of x at 1, because the top is 0 at 1, it means x minus 1 is a factor. So if I factor the top, I get the common factor x minus 1. This is a situation we're familiar with. We've looked at several examples of that sort, where we are looking for limits of functions when we have an undetermined situation of the type 0 over 0. We know that we can cancel the common factor x minus 1 without changing the limit at 1. We obtain the limit at 1 of 2x plus 5 over x plus 2, but this is a rational function that has 1 in its domain, so to get this limit we just plug x equal 1 and we get 7/3. The important point is not that it's 7/3, but that the limit is not infinite. the regular limit exists and is 7/3, in particular both one-sided limits are also 7/3, so none is infinite. Therefore, x equal 1 in this case is not an asymptote. What happens on the other end near x equal -2? Well, if x is close to -2, then x plus 2 is close to 0, and therefore the bottom is close to 0. On the other end, if I plug x equal -2 at the top, I get 4 for -2 squared times 2, 8, minus 6 minus 5, so 8 minus 11, -3. So at the top gets closer and closer to -3 as x gets close to -2, and the bottom gets closer and closer to 0. So I have a non-zero value divided by something getting closer and closer to 0, and that will lead to an infinite limit. In other words, x equal 2 is a vertical asymptote. Now in this particular example, we may ask, while we're at it, what is the limit of f at -2 from the right? We know that we're going to get an infinite limit, but is it positive infinity or negative infinity? To answer this question, let's look at the sign of the function when x is close to -2 but greater than -2. In that case, x plus 2 is a positive quantity, right, if x is greater than -2. On the other hand, x minus 1 is close to -3 because x is close to -2, so certainly it is a negative quantity. That means that the denominator as a product of a negative and a positive factor is negative. On the other hand, the numerator, if we plug -2, we have seen that we find -3. In other words, as x gets close to -2, the top gets close to -3, so it is negative as well. So I have a quotient of two negative quantities that is something positive. So as x is approaching -2 from the right, this quotient is positive. Since we know that we're going to get an infinite limit, we obtain that the limit at -2 from the right is positive infinity. Let's see another example. The function is x squared plus x minus 6 divided by x squared minus 4x plus 4. As in the previous examples, we know that the only place where we may have a vertical asymptote is for values of x that make the denominator 0, because these are the only places that may be outside of the domain of the function. So we look for the zeros of the denominator, and we see that it factors as x minus 2 squared. In other words, x equal 2 is the only possible vertical asymptote, but again, we may want to check what happens at 2, because we may have again an undetermination of the type 0 over 0. And indeed, if we plug x equal 2 at the top, we get 2 squared is 4, plus 2 6, minus 6 0. So we have again 0 over 0. Before we conclude that x equal 2 is not an asymptote, we need to really look at what happens in terms of limit at x equal 2. So the top is 0 at 2, that means I can factor it, and I know that one of the factors is going to be x minus 2. Here is what I obtain. And you see that after we cancel the common factor x minus 2, we obtain x plus 3 over x minus 2, and the bottom is still 0 when x is 2, while the top now is going to get close to 5 as x gets close to 2. In other words, when x gets close to 2, the top gets close to 5, the bottom gets close to 0, and therefore we get again an infinite limit. Therefore, x equal 2 is an asymptote. Now we're going to turn to the next video to look at another kind of infinite limits. Instead of looking at the finite numbers where the function goes to infinity, we're going to look at whether the function goes to a finite number or approaches finite values as x grows without bounds.